not allow this to occur, but the acyl chloride or the acid halide allow it to occur. Everything has to do with stability, so that's a bit too vague. So maybe the first thing to address would be, how do we go from the ketone to the enol? Like maybe if we can figure that out, we can then apply that information backwards, okay, or forwards to the question being asked. How do we go from the keto form to the enol form? What has to change? Okay, we have to remove a hydrogen. What hydrogen are we removing? Where is that acidic hydrogen? The alpha carbon, so we will remove one of those hydrogens. How can we remove that hydrogen? Let's actually take it to the enol late. Might make this a little bit easier. How do we remove that hydrogen? We need to add a base. So we add a base, which can share its electrons with the hydrogen, but now the hydrogen has too many bonds, so what has to happen?
Kick them back.
We have to kick some electrons away from it. So we can make the pi bond, but then our carbon has too many electrons. And we would end up with the enolate. Make sense?
And another H plus.
That is our keto enol tautomerization. So when we're looking at the Hell-Volhard-Zielinski reaction, we're doing some kind of crazy, bizarre stuff, and it all centers on the ability to enolize. The carboxylic acid does not enolize, yet the acyl chloride does. So the question again comes back to why. Well, now that we know what the tautomerization is, okay, we said our hydrogen was alpha, right? Do we have an alpha hydrogen? Yes. I have alpha hydrogen in both cases. Right? So you're right. We needed an alpha hydrogen to do the keto-enol tautomerization. Both of them have it. Okay, what else did we need to do our enolization?
Base.
We needed a base. Okay, so what happens if we add a base? What do we want that base to do?
Take a hydrogen.
Take a hydrogen. Which hydrogen should it take?
Should take the. It'll take the one on the OH.
What hydrogen will our base always react with? The most acidic. Which is most acidic? Our carboxylic acid. So it would remove that, and at best we would then convert down into this structure, our carboxylate. Do we still have an alpha hydrogen? Yeah. We even have base. We could even say we still have tons of base left. Okay. Why does the carboxylate not enolize?
Because the carbon isn't positive enough to make it acidic.
Why is the carbon not positive enough? That negative oxygen stabilizes, okay, nullifying the ability to do the resonance stabilization in the enolate. Without that resonance, I cannot do the tautomerization. If I start with a carboxylic acid, no tautomerization. I have that negative of my carboxylate. That carboxylate or negative oxygen stabilizes it. This prevents carbonyl resonance, okay, or enolate carbonyl resonance, which then means that red hydrogen is not acidic, and we can now call it a purple hydrogen because it doesn't match our keto form. Well, why does the acid chloride allow for enolization? Why is that hydrogen acidic? So number one, if we add our base, The base can't react with the chlorine because, well, chlorine is not an acid. Okay? So it doesn't react there. The only thing it can do is react with that hydrogen, which could then share electrons inwards. Okay? So our acid chloride, even though it's an acid derivative, our acid chloride is enolizable, while the acids, carboxylic acids, are not. Okay? And they're not because of that extra strong resonance, because of that acid-base characteristic that happened first. Kind of makes sense? Okay. Saying some head shakes yes, so now we're going to do a comparison here. I want to know which one will enolize faster. The aldehyde or the acid chloride? Do they both have an acidic hydrogen? Okay, they both have that alpha hydrogen, so both of those could potentially be removed. Okay, what's going to make one of them react faster than the other? If it's more acidic. Okay, so what we're really asking is not which of these forms the faster enolate, but which is actually more acidic. How do we determine acidity?
Ability to stabilize.
The ability to stabilize, okay, our negative charge. So the first thing we would look at is charge. So if I removed the hydrogen, I'd be looking at my conjugate base and trying to evaluate through that. Okay. Charge. Are they both charged? Yes. Okay. How about atom size? It's the same. It's carbon versus carbon. There is no difference. Atom electronegativity. Same. There is no difference. Next one is resonance. Do they both have resonance? Yes. There is no difference. It's the next one. An inductive effect. Is there an inductive effect? Yes. What is that inductive effect? Chlorine is more electronegative than hydrogen, meaning the chlorine starts to withdraw electrons, which then means our negative gets drawn into the structure. The more drawn into the structure it becomes, the more stable the conjugate base. The more stable the conjugate base, the more acidic the original hydrogen was. Okay? That ranking of acidity or acid strength is what we did in first semester. Okay? We're now applying it to a new situation and looking at how that then changes the reactivity in this particular case, what we can do with that further on down the line. So you have to be constantly applying everything we learned in first semester. It's not just, oh, it's new semester, so new stuff. It's all old stuff. You're just stacking it. Okay? Questions about that? Yes?
On the first one, you took the left hydrogen because those are the alpha hydrogen. The one on the right's not alpha, right? It's not an alpha hydrogen.
That is true. The one on the right, our red hydrogen, is not an alpha hydrogen because it's directly attached to the carbonyl. At best, it's a 0 carbon. Okay. Why is that hydrogen, since you asked, not acidic?
It's not stabilizing the negative charge.
Okay, so we aren't looking at that negative charge. We're saying, why is that hydrogen not acidic? What happens if we removed that hydrogen?
You get a negative on the carbon.
Is that negative charge stabilized? Okay, I heard yes and no. If we said yes, how would we stabilize it? What are you thinking to stabilize that negative charge? Try and do resonance, triple bond. So let's share those electrons in to make a triple bond. What would the result look like? 1, 2, 3. Oxygen, 1, 2. Right?
Yeah.
There's no plus sign. That oxygen has 10 electrons around it. What I did was an invalid maneuver. There is no resonance to stabilize that negative charge. Okay, what does that mean? This structure is bad, which then means, well, that actually kind of works. We can't remove that hydrogen. Okay. Anytime you're thinking about trying to create a nucleophile by removing a hydrogen, remove it. Prove that that structure is valid, that it can exist, that it is stable. If you can't prove it, then you can't do it. Trying to come up with some weird rhyme there, but no. Okay? Kind of makes sense? Okay. New stuff. There's a section on the sulfonyl chlorides. These are kind of, we've already talked about them. Remember when we addressed, whoa, sorry, my screen's freaking out. It's really freaking out. We addressed, come on, this far right structure. Remember back in the slides we talked about something that looked like this? And I said, what if whatever that squiggle was a chloride? What did we have? That sulfur then acts as an, not to give away too many hints, an electrophile. Okay, that sulfur can now accept electrons because the chlorine and the two oxygens are all drawing electron density away. Okay, and I said, well, what if it wasn't a chlorine? It was instead, whoops, it was instead an OH. Now what does it act as? Now we have a carboxylic acid in that purple hydrogen because everybody's favorite answer, resonance. Okay, tons of resonance to stabilize that. Okay. So our sulfur compound is neat because it can expand its octet, it can do all sorts of other fun things, we can attach lots of electronegative elements to it, and that changes its reactivity. And Tanisha, I'm going to throw you under the bus partially right now. Sorry. We've seen this kind of compound show up before. We've seen it show up in, say, this structure. What is the name of within that red box, Tanisha? Close. Sulfuric acid would be this guy. If I get rid of the purples, the purple hydrogens, it becomes don't tell me furic acid. Sulfate. It's the sulfate ion. Okay. In all of these cases, that sulfur, as soon as we attach those oxygens, now becomes incredibly stabilized through resonance, which means what happens to the nucleophilic character of a sulfate? There is now so much resonance that the sulfate ion cannot act as a nucleophile. It cannot act as a base, which is why when we look at sulfuric acid happens to be a stupidly strong acid because it generates a stupidly stable conjugate base through all that resonance. Okay? If we tweak the structure somewhat and we draw in a chloride, okay, well, what's different about the chloride from the oxygen? The chloride doesn't do resonance. Okay? That then puts the sulfur at a disadvantage. It now has a whole bunch of electronegative elements around it, but it doesn't get that extra stabilization from resonance, which then means it's looking for a different atom to come in and get rid of the chloride so it can get more resonance. It can stabilize, which means that sulfur now acts as a what? An electrophile. Okay. It is dying for more electrons, a alternate source of electrons than, say, a chloride or a bromide or an iodide, because none of them do resonance to stabilize. But an oxygen would do resonance with it. A nitrogen, that would do resonance with it. Okay, so it's looking for an electrophile, which makes it act as, Corey? An electrophile. Just giving you the opportunity to change your answer. Okay? So all of these reagents are great electrophiles, and they all share commonalities. Okay? We have, number one, the chlorine attached, which is our great leaving group. We have the carbonyls of our oxygen. We, in fact, have 2 carbonyls of our oxygens, which makes it even more electrophilic. And then we have some other group attached to the side of it. Okay? And the first one, it's a methyl group. Okay? Well, methyl doesn't really supply a lot of electrons, which would suggest our sulfur stays kind of electrophilic. But when we move to the next one, is it just a methyl anymore? No, what is it? There's a bunch of fluorines. We can actually cheat and use the naming that's written there. That one we said was methyl. This is trifluoromethyl. Okay? Also known for some stupid reason as, maybe I shouldn't say stupid, trifluol. Why? I don't know. Somebody thought it sounded cool. Okay? What can you tell me about the reactivity of the trifluol chloride? I have a good leaving group with the chloride, but I still had a good leaving group on the other side. Oh, with the CF3. The CF3 will not act as a good leaving group, actually, believe it or not. Yeah, it won't stabilize that negative charge very well. The fluorines are too electronegative. I now have an electron withdrawing group. Those fluorines withdraw electrons from that carbon, which then withdraws electrons from the sulfur. So what can you tell me about the sulfur in the trifluol chloride versus the methyl chloride? It is more electrophilic. Okay? So we can take advantage of that chemistry in different situations depending on what we're trying to do. The last one, we have that big benzene ring, which can contribute a lot more resonance, which does a little bit to stabilize that sulfur. Officially, if we compared the tosyl chloride to the methyl chloride, which one would you expect to be the stronger electrophile? Why the methyl? I could come up with 2 explanations for this that are counter to each other, so I'm just interested. So steric hindrance doesn't really contribute to an electronic effect. Okay? It just says it doesn't work. Okay? So if by that token you're saying that the tosyl cannot act as an electrophile, well, that's not true. It can. Okay? So it's not a steric effect.
Conjugation.
Okay, conjugation. What is the conjugation going to do to the system?
Make more stable.
Okay, we could potentially shuttle those electrons out, making it more stable. So we could come up with an explanation for why it's less electrophilic. Can anybody come up with, and this is the harder one, come up with an explanation with why it might be more electrophilic?
Which one? The methyl?
The tosyl. Why would the tosyl be more electrophilic than the methyl? As a hint.
That's a very stable bond.
Not quite.
Is there resonance?
Resonance is what Tyler suggested. That stabilizes it. What is the hybridization of that atom? What is the hybridization of the methyl? Conjugated system still goes back to making it less electrophilic.
SP2 would be, has a more electronegative.
SP2 is more electronegative than SP3 because it has more S character. We could come up with the argument that we have kind of an electron withdrawing effect here because of that SP2. I would probably argue resonance instead of the hybridization because resonance is further up on our list of priorities in the hybridization. I would lean towards it being less electrophilic than the methyl because of the resonance effect. Okay. Trifluol's the most. Yeah, methyl's the one in between. Okay. We've got an example reaction shown below. Pretty sure we saw this mechanism when we first looked at this reagent in step 1, in unit 1. Okay. So we probably saw it then. It was a bit premature. Okay. We saw it in that case because what we were trying to do was activate our R group by making a good leaving group. Okay, but to get it on there, we had to go through a nucleophilic addition and a nucleophilic elimination. Okay. So I don't remember the detail of when we looked at that mechanism, if we actually looked at that part of it, or we just said, hey, it goes on. Okay. But the mechanistic steps are ultimately the same deal. Notice in all of that, we didn't mention pyridine. What is the role of pyridine here? A proton acceptor. It's acting as a base just to remove the hydrogen from our starting alcohol so that we have our neutral structure. Okay. So you'll typically see some kind of base supplied in there, usually a weak base. Why a weak base and not, say, a strong base? It's always difficult to come up with that, so maybe we should name a strong base. Give me a strong base. Sodium hydroxide. Why not add sodium hydroxide? Sodium hydroxide is a strong nucleophile. More than likely, it would react instead of the alcohol. Okay, so when we add a base, we need to be adding a strong base that is non-nucleophilic. Because if it's nucleophilic, it reacts with our sulfur compound instead of our other reagent. Okay, so that's typically why you'll see pyridine show up. Pyridine works as a nice liquid solvent, and it is also relatively basic but non-nucleophilic. And it is non-nucleophilic, Nicole, because you said the answer earlier. That's why I went back to you.
Pyridine is non-nucleophilic because of what?
Yeah.
Sterics.
The pyridine is typically non-nucleophilic because it's fairly large and bulky, so it's got a decent steric hindrance effect going on with it. Okay. So, why not? Let's do another quiz. Sideways, Jen, what did you say earlier that I told you I wanted you to repeat?
They're all doing the same addition.
And in explaining, I think to Nicole or Laura, you said something similar to that? They're all doing the same thing. Everything within this section is doing the exact same thing. Okay? Everything. Same thing. If it is not repetitive yet, you have not done anywhere near enough practice. Okay? Everything drawn out as our products should be like, this is dumb. Why do I have to draw this again? Okay? That is where you need to be at this point. If you're not there, you have not done enough practice. Okay? The homework, the online homework, despite what I've been hearing about how much trouble that's been causing, that is your skeleton base level. You finish that appropriately, maybe you pass. You want higher than that, you need to be doing more practice than that. Okay? These need to be fast, and it needs to be, oh God, are we really doing this again? This is dumb. I already know these answers. That's the reflex that you need to be at within this reaction. We've now spent probably 6 weeks looking at these, and we still have another 2, okay, of doing these same stupid things. Okay? Questions about any of those? Yes, and then Tanisha.
From like number 3 and number 5, do we not need to push the other part of the product?
So that's a good point. In number 3 and number 5, I split it and then didn't even bother to draw the other half. Okay, the other half should technically also be drawn. Okay, but it just kind of comes down to laziness. It's one of those, it's the bigger half, so I'm drawing the bigger half, which doesn't always work. Okay. Sometimes in these reactions, you'll just see it drawn as one of the products in your multiple choice. Sometimes you could be given both, and you have to answer for both. Depends on the question being asked. Tanisha?
That was my question.
Oh, okay, cool. Well, there's an interesting question. Why 2 equivalents? Anybody get a good answer on that one?
Because it's not a very good nucleophile.
It's actually a better nucleophile than oxygen.
One acts as a nucleophile.
Yes, one acts as a nucleophile, the other one acts as a base. Nitrogen is a really good base. Once it comes in and one equivalent reacts, we then have an acidic spot or an acidic hydrogen. The base comes in, or nitrogen comes in, removes that hydrogen. Well, oh crap, we now don't have a nucleophile. We end up losing our nucleophile equivalents unless we have a second equivalent. We typically see that show up with the nitrogen nucleophiles, though theoretically it could happen with any of the others, with the oxygens as well. Okay? We typically don't reference it with the other ones because water. What is the concentration of water that we're adding? Usually adding vast excess of water. Why vast excess of water and not vast excesses of the amine? It should only be aqueous when we run the reaction. Water is not a super strong nucleophile, so we could come up with an explanation along those lines. There's another one, or at least two more. Water is free, which means I don't care how much I use. I'm going to dump tons of it in there. It's going to react in excess, and I don't have to worry about it. Okay? So water being cheap is really easy to toss in there. Most of our alcohols tend to be on the cheaper end of the spectrum. Two of them shown up there are probably not very cheap. Okay? 1 and 3 are probably not the cheapest alcohols on the planet. Okay? There's another reason why in 4 we would not have vast excess. What do amines smell like?
Rotting fish.
Rotting fish. Okay? We tend to avoid amines because they stink to high heaven. Okay? So we tend to only use just enough to get our reaction done and no more than that.
Oh, that's what your product smells like?
Yeah.
Huh. That could be useful information. Okay? So having some idea of what the functional groups smell or physically appear as can be helpful in predicting some things. Okay? We do have some names of our nucleophilic addition and elimination reactions. So the big common ones that you'll see pop up are transesterification, which we did with reaction 5, and saponification. Transesterification. What does trans mean? Opposite. Esterification. Well, what does ester mean? What's the name of a functional group? Ification? Creating. Okay. So I am creating an ester, but it's a trans ester. So I'm creating a new ester. What happens in the transesterification? I start with the ester methyl benzoate. Okay, there's the basics of my ester. And what changed? The methyl becomes something else. I have a new ester. That gets referred to as a transesterification. How do we do that? Okay, well, we need something to react with our ester to begin with. How does our ester to begin with react? As an electrophile, we have that partial positive, which means I need to add a nucleophile. And since I know I'm trying to do a new ester, that nucleophilic atom must be an oxygen, because if it wasn't an oxygen, it wouldn't be an ester. Okay? And since it's a transesterification, I'm changing the ester. Whatever that oxygen is connected to must be different than what our original oxygen was connected to. Okay? Notice in this case we ran under what conditions? Basic. How do we know it's basic? We see a negative charge. That negative charge should immediately be a tip-off that we're running under basic conditions. Could we do this under acidic conditions? Yes. Yes, we can. When we run under acidic conditions, what's going to change? Well, now we have a crappy nucleophile, so under acidic conditions, no good nucleophile. Well, then we might say, yeah, that's not going to work. But under acidic conditions, what happens? You protonate the carbonyl, so under acidic conditions, what happens? We make our electrophile more electrophilic. Under basic conditions, we have a more nucleophilic nucleophile. Huh, that sounds familiar, because we said that exact same thing in the last unit. The last time we looked at acidic and basic conditions of carbonyl reactivities, because it's the same. Right? There's that internet meme, same, but different.
Yes. Interview.
Where is it from?
The interview with James Franco.
Yeah. Sorry, I'll find that picture later. Saponification. Okay. This one, admittedly, is going to be a bit thin. Saponification. Soapification. What are we making when we do a saponification reaction? Soap. That's the whole point. Okay. Soap is merely a carboxylic acid that has had the hydrogen removed. Okay. So we would have an exceptionally what molecule? Basic is not a good answer. Yes, it is negatively charged, but it is not a good base because there's resonance. We would also know it's not a good base because what was the starting functional group? A carboxylic acid. It's called an acid because its conjugate base is not basic. Okay. If its conjugate base was basic, would we have an acid? No. Okay, that goes with those partnerings. So we have an exceptionally polar molecule in our conjugate base. Okay, so that's cool. We could add soap to our hands and we could dissolve polar substances off of our hands. But what does water do? Dissolve polar substances off of our hands. So clearly adding soap doesn't help us remove. What else does our soap have? A big long carbon chain. What's that big long carbon chain? I know that looks slanted. Just twist your head.
Toothbrush.
If this end is polar, you have a really weird toothbrush. If that end is polar, what does the carbon-hydrogen chain have? Non-polar. We have a single molecule now that can interact with both non-polar species and polar species. What is water? Polar. So our soap can interact with water, which is great because we can then wash the water and the soap off. What does the non-polar end of our soap interact with? All the junk on your hands that you're trying to get off. All the non-polar stuff. Okay? So that's kind of our quick and dirty realization of what's happening within soap. So when we're looking at a saponification, we typically add a strong base. Why a strong base? What hydrogen is there on ethyl ethanoate? It's a strong nucleophile, okay? Not so much that it's a strong base. We are running under basic conditions, but it's acting as a nucleophile. It can attack, kick up, bring the electrons back down, kick that out, and we would end up with the carboxylic acid. And would that be a favorable reaction? Negative oxygen, negative oxygen. That's an equilibrium at best. That says no real high yield. Yet our yield is relatively high, 87. Nope. Nope. This is a relatively strong base. This was an acid. What happens? It deprotonates to form the carboxylate salt. The carboxylate salt, come on, there it is resonance stabilized. That's what drives this reaction forwards. Much the same as our reaction of our amides in the presence of a strong negative nucleophilic oxygen. Okay? We need that secondary step. Okay? Because that secondary step is happening, do I have the product in one step? No. What do I have to do? That's why I add the acid, to put the hydrogen back on. Okay? Do you guys need the mechanism? Thank you. No is what I wanted because I really didn't want to show it. Your textbook does show it, okay, but we could go through and draw it all out as well. This one's being shown under acid conditions. The first step of our acid conditions is going to be to protonate our carbonyl compound with our acid, right? That gives us a very good or a much better electrophile. I know I said I wasn't going to show it. I'm not going to show it all, I promise. With resonance gets us set up with a stronger, I already forgot what was up there, it's an H. Gets us a stronger electrophile. This can potentially react with water if we wanted to do a saponification. Though saponification implies base. Okay? Or it could react with another alcohol, okay, to get us a transesterification and change that ester into something else. Okay? Kind of makes sense? Realize within this you will have several protonation, deprotonation steps. Why? That's typically what comes with acid mechanisms, which you should also remember from the acetyl mechanism that we did in the last unit. Okay? It's the same general idea. We have to worry about a lot of those protonation, deprotonations. Okay. This is a fun one. Can anybody tell me what happened here? And hopefully I can change this before you guys read anything. Not that the reading is really going to help. What changed? I heard something about an oxygen. I like that description. Somehow or another, an oxygen climbed in there. Okay. Unfortunately, that is not a valid mechanistic step. So somehow or another, an oxygen made its way into that structure and kind of split that open. Okay, that's really, really weird. Okay. What do you guys think? Any ideas? What's that?
Like if you're looking at the reagent that it's going to react with,
Yeah?
you need an oxygen attached to the phenol group, but there is not one.
So I see what you're thinking. You're thinking like a transesterification. Did we start with an ester? No. So unfortunately that doesn't work. We're starting with a ketone. So we can't actually just have an oxygen come in and attack. Even if we had somehow supplied that entire piece, okay, even if that had come in as, oh geez, that's big, and came in and attacked, we would form our tetrahedral intermediate, but then there's no leaving group. So I couldn't possibly just run it that way as an esterification reaction. Okay, so that doesn't work either. Other ideas?
I see down there at the bottom, we have, what is that? CH3, this
That was our trifle, whatever the hell it was. Okay, except when we looked at it before, it was this, with a Cl. And then it was a great electrophile. Is it Cl? No, it's got an oxygen. Is it just an oxygen? It's also got an H. What do we have here? It's an acid. We're adding actually a pretty strong acid here. Okay. That's interesting. What can we do with that strong acid?
protonate your ketone.
Okay, we could go through and protonate the ketone. And I really don't feel like drawing out those rings. What's wrong with that drawing? Corey?
Positive.
We have a positive charge on that oxygen. We do have resonance stabilization. I also don't feel like drawing arrows right now, but I will in a second. What do we now have? We have a good electrophile. Okay. Good question. Oh, but you asked me first. Okay. Now what? Do we have another reactive species? Yes. Yes, we do have another reactive molecule in there. What's that other reactive molecule, Tyler?
I'm stuck between the ketone, sorry, not the ketone, the carbonyl on our NCPBA or the OH on our NCPBA.
Ah, okay. I like that idea. We've got the carbonyl on our MCPBA, or we can reference the OH on the MCPBA. What do you guys think?
More resonance on the carbonyl,
There is resonance with that carbonyl, yeah.
less likely to react there.
So we could think about that as less likely to react because of that resonance. It's a possibility. So there's another theory. If we looked at our ketone compound, it's going to act best as an electrophile, which then means the carbonyl, its chemistry is electrophilic. So that's another good reason to ignore the carbonyl. There's another good reason to look at that oxygen. What is that oxygen bound to? What else is that oxygen bound to? Another oxygen. What can you tell me about that bond? It is exceptionally weak because we have two electronegative elements attached to each other. Okay. What can happen? I'm not even sure if I'm drawing this right. I'm hoping I am. So you may not actually want to copy me. And then, oh my gosh. It's like a little Casper, right? A little friendly ghost. Maintain the theme. You don't see the ghost? Little eyes there. It's got a little frowny face. Look at my nose. Okay, now what? What's wrong with that structure, Corey?
Man, so you're trying to see where the positive charge would be. Oh, there it is.
We have the positive charge. Does oxygen want to be positive? No, what happens? I'm not about to draw the ghost again.
Take away the hydrogen.
We can take away the hydrogen. Okay. So cool, now the oxygen's a little bit happier, but did we resolve the number one issue? What was our number one issue? Good question.
Still have the OH.
We still have that OO bond, which we said was exceptionally weak. So should the other oxygen attack? No, that's not going to work. Okay. What does this group look like? A great leaving group. We need something to cause it to leave. Hydrogen wouldn't cause it to leave because hydrogen comes off as a positive. It doesn't work. We need something to force those electrons to go that direction. But then I'd have a positive oxygen chilling over here. I can draw on purple right there. And that's bad. I can't do that.
Second equivalent of your electrophile.
Could add a second equivalent of the electrophile, but that's not going to supply electrons. The electrophile would provide positive charge. Where else do we have electrons?
CH2CO2?
No, that's our solvent. We can remove that because it was acidic. Our oxygen was positively charged.
Isn't there more of the reagent?
Are you suggesting we have more hydrogen?
We have a tetrahedral intermediate. What did our tetrahedral intermediates typically do?
Kicks back down.
They kicked back down. So our electrons come back down. But now what's the problem?
We don't have a leaving. Well,
We do have a leaving group. We could kick that out.
but we just
Ooh.
have that. So
Yeah, so that doesn't work. The wrong thing. Oh, stupid letters. The wrong thing is leaving.
Take one of the phenyl groups.
Say that again.
Take one of the phenyl groups.
Or in this case, one of our R groups. Let's take those electrons and kick those out. But then I'd have a carbon nucleophile, C negative. Ooh, that's bad. Nah, can't do that. I wonder if there was something positive nearby that I could immediately shuttle those electrons to. Like that. Whoa.
there's no positive oxygen.
Don't do that, whatever you just did, computer. No, it freaked out, but it didn't freak out on you guys, so it's okay.
But then what happens to this?
Well, what's the result of that?
We get a carbon.
We've got our carbonyl. There's our R group. The other R group moved.
Yeah, how does the whole R group?
We saw that before.
Phenyl shift.
It's a shift. It's a rearrangement.
So should that arrow
are we going to the oxygen then and not to the
Oops,
bond?
yeah, not to the bond.
That was my
Yeah.
confusion.
I've got half a dozen different things drawn on the screen right now. It's not easy to figure out where things are.
Okay. Oh, that looks good.
Yeah. Okay. This is why it gets named for barophilic. Okay. It's doing some really crazy things within this.
So how can we keep losing hydrogens without them going somewhere?
The hydrogens get picked up by something remotely basic in solution. So we've talked about this throughout the whole semester. Hydrogens on and off the structure pretty much at will. The only time we have to be careful of is we can't add them to the structure if we're in basic conditions. We can't remove them from the structure if we're under acidic conditions.
So since we're in acidic conditions.
Right. It's acidic conditions, we can't add or remove and it depends on the acidity. The hydrogen that you were concerned about initially was the hydrogen off of this oxygen, which I'm not going to attempt to draw on there. That one is acidic because the oxygen would have been positive. That's fine to remove. Okay. When we bring this back down, we'd end up forming. This looks horrible on my screen. I'm glad it doesn't look horrible up here. We'd have that structure. What can you tell me about that hydrogen? It's stupidly acidic because the oxygen doesn't want to be positive. So we can follow through one more step out to our final ester. Okay, does that make sense? Okay. When we, oh, don't do that. Oh, that's right, because my screen freaked out. Okay. The interesting feature of our ketone here is that it is symmetric. What happens if it is asymmetric? Well, which group moves? Because we have a tetrahedral intermediate, both phenyl rings are equally likely and probable to move. But what if that becomes not a phenyl, but a CH3? Okay. What if I make that a CH3? Well, now which one moves? Okay. Which should be the ester? I don't know. Okay. That depends on the reactivity of this. The oxygen will insert itself according to what is known as the migratory aptitude. Okay. I have not found out a good explanation for this, unfortunately, yet. Okay. What is the migratory aptitude? Hydrogens very likely to migrate. Okay. You might say, well, hydrogen's incredibly small, so the next most likely thing to migrate, particularly since I'm looking at a phenyl ring and a methyl group, would be a small group, right? Like a methyl. Methyl should shift. Yet, what's the next thing on the list? An aryl group, which is the aromatic ring, which is really big. Okay, well, that's a bit weird. What's the next part? Tertiary group. The next one, secondary, primary, methyl. Methyl groups have the least likely aptitude to shift. Okay, which means when we look at our product now, the product we would end up with would be this one. The phenyl ring shifts, not the methyl, and I would end up with that new product. Okay, which I modified, and we should ignore those names. Okay. I have no explanation for that. That makes absolutely no sense to me. Okay. And so, unfortunately, I got nothing better for you than you are responsible for knowing that. Okay. You need to have that trend memorized. You could start with hydrogen and then just biggest to smallest after that. So hydrogen is the exception. The bigger the group, the more likely it moves after that. Okay. If you want to talk to me about trends that you think you see within it, I'm more than happy to talk to you guys about it after class, but that just kind of sucks. Okay. If we look to the mechanism, which we already did, so I don't actually need to stepwise through all this. Okay. We can go through it and evaluate it. Your textbook draws it out a lot cleaner and prettier than I did, and they show all the deprotonation steps along the way. Okay. Aldol condensations, right? You remember all this? We had the base. Oh, we actually kind of started with this. The base does what? Removes the alpha hydrogen to give us the enolate. We're doing a keto-enol tautomerization in that first step. That enolate is special because it is a nucleophile because of our negative carbon. What is special about our starting aldehyde? It's an electrophile. What happens? The nucleophile attacks our electrophile. And we end up with a negatively charged structure. Without our hydrogen, we could add that hydrogen on and we would have what product? The aldehyde followed by an alcohol, and we'd have the, I don't know why I wrote it like that, the aldol. I should flip the structure. Our aldol, right? Just reading, combining the names. Some people are amused, some people aren't. Okay. That is then followed by our condensation reaction, okay? And we have altogether our aldol condensation. For this to work, I had to have an enolate. Okay? I had to have enolizable hydrogens. But we said carboxylic acids were not enolizable. Are other acid derivatives enolizable? How about esters? Are esters enolizable? As a hint, yes they are. That's why it's not referred to as an aldol anymore. If we run an aldol reaction with an ester, it's known as a Claisen condensation. Why? Because we didn't use an aldehyde or a ketone, we used an ester, and that somehow deserves a new name. It is identical chemistry. Right? So when we looked at the aldol, let's draw out our shortcut real quickly. Okay. We've got our nucleophile drawn on top with our negative. We could draw our electrophile underneath. And what happened? There's the result of our aldol. Okay, a full aldol condensation. What happens with the Claisen? Well, I want my nucleophile again on top. Where's the nucleophile? Left or right?
It'd be the right.
The rightmost, because that's the only one with alpha hydrogens to the carbonyl. What do I need to draw underneath?
What's reacting with?
What it's reacting with. What do I then need to do? Okay. I could then theoretically take that out, whoops, and link the two. However, this does something slightly different. What is that slight difference? When it attacks, we'd form our tetrahedral intermediate, right? And in the case of the aldol, when we formed that tetrahedral intermediate, there was nothing that that structure could do. Okay? We can't reform the pi bond. That can't happen. So it picks up a hydrogen. We still have an acidic hydrogen up here, and we could then kick that out as a leaving group. Right? That was our aldol. What happens with our Claisen? Which then means the product I get is not the exact same as the aldol. I get a dicarbonyl. Okay? Because of the leaving group presence. Okay? So the chemistry is effectively identical. It's just what happens in that last step. We don't end up doing a clean standard alkene formation for our condensation. We end up reforming our carbonyl. Why do we reform the carbonyl? Well, I have a leaving group. Okay, the leaving group kicks out, and I can reform the carbonyl instead of doing the alkene. Okay. So, actually, there it is. There's our product for that reaction. Okay, does that look pretty? It can look pretty, so it doesn't look pretty now. Okay, so let's make it look prettier. And we've now got our structure. That was one piece. This is from our second equivalent. What did we lose off the second equivalent? The other ester functionality. Right. Recognizing the pieces, seeing where they're coming from, and kind of pushing them in or out. Kind of makes sense? Ta-da! What the heck? Oh, I'm asking for the complete mechanism. We will start Monday with the complete mechanism. That's a lie. It's there. We'll not start Monday with the complete mechanism. Okay? The mechanism is in your textbook. I've shown all of the basic pieces. You know how to do it from the aldol. You're doing the same thing with the Claisen. The one big difference between the aldol and the Claisen is step 3. That is because we can reform our carbonyl, and we now have a leaving group that I can kick out. Okay. That generates these products. Interesting feature of those products. Are they more or less stable than what we started with? Trick question. Neither. They're neither more stable nor less stable. Which means, what are the odds I'm going to be able to get the Claisen reaction to work? 50-50 at best. I get very low yields. Except, when we run the Claisen, we get exceptionally high yields. Okay, or much better yields than 50%. Why? Nope, not the acid workup. We have a base, and we have an alpha hydrogen. There's no pineapples. We have an alpha hydrogen that is acidic. The base removes that, and I generate this structure. What is special about that structure? Yes, it is a carbon nucleophile. What else is special about it? It is resonance stabilized. Is that step reversible? No. That's what drives the reaction. I need a second alpha hydrogen for the alpha Claisen or the Claisen condensation to work. If there is no second alpha hydrogen, the Claisen condensation does not work. Right? That is a pretty big deal as far as this reaction goes. With that said, where we will start on Monday is here. Okay? And I'll give you the first 5 minutes of Monday to answer these questions, which is really written as 3. So I want the product for the first one, and then I want 2 possible products for the bottom one. Okay?